My name is Jason Forthofer. I'm going to be talking today about fire behavior outside model capabilities. I work for the Missoula Fire Science Laboratory as a research mechanical engineer. I also go out as a division and a fire behavior analyst. So I kind of have the research side and the more operations side of things. You guys have been going through a lot of stuff in this S490 class. The whole point of my presentation is that you guys are really aware of a lot of the phenomena that happens out there that is not accounted for by the models. So we're just going to go real fast through this and just touch on a few of these points that you should really be aware of. So this can help you both in your actual modeling, but even better, it can help you when you get out there on the ground. You're not using a computer or anything, but you're using your head to try to do predictions of fire behavior. Fuels, weather, topography, that's a great way to start when you're thinking about any fire behavior, or if you're giving a briefing or anything, touch on these topics. If we delve a little bit deeper, I'll show you a couple examples right now that fuels, weather, and topography isn't everything when it comes to fire behavior. First, we're going to look at this overhead video of two fires spreading in wheat stubble. And there's a wind coming from the kind of upper left of the screen, moving down to the lower right of the screen. The only difference between these two fires is that one was ignited as a line fire on the left. You can see it, it's going to start filling in here in a minute. And the right one was ignited as a point fire. But as far as fuels, weather, topography, for each of those fires are identical. Same wind, slope, it's flat ground, same fuel, same everything. Your inputs, if you were running, say, Behave, the Rothermel model, your inputs would be identical for these two fires. But as you watch these two fires, you're going to see they spread very differently. That line fire, in this case, is spreading about 3 times faster than the point-ignited fire. The question is why? What's going on there? Rothermel should tell us these two spread the same. So let's look at another example here. So this is in a laboratory. This is a big bed of shredded wood. And we're going to ignite this where that guy's standing there. This is going to be a head fire, so the wind's blowing kind of from the lower left to the upper right. It's a little bit hard to see, but when they ignite this, you may notice that when the fire first starts, it spreads slowly and it takes a while to increase in spread rate, so it's kind of going to accelerate its spread rate. The point here is that as that fire burns down that bed of fuel, the fuels, weather, topography at any point in time or any location are the same, but the spread rate varies down the bed. So there's something else going on here other than just fuels, weather, topography. So if we look at a plot of spread rate at different locations down that fuel bed, so the x-axis down here is the position down the fuel bed, and the y-axis, what we're plotting here, is spread rate, and that's a bunch of different burns down there. But if we just concentrate on the red line, which is kind of the average of several burns, you see something kind of interesting, don't you? The spread rate changes at different locations down the bed. And again, it's the same fuels, weather, topography. In this case, there's at most a 3 times difference in spread rate there. When the fire first starts, it's spreading relatively slowly, and it pretty quickly accelerates, and it kind of accelerates to a peak and kind of overshoots maybe what you'd call the equilibrium spread rate, and comes back down then, and eventually maybe it's kind of coming to a steady spread rate after a while there. So what the heck is going on here? In all your 190, 290 classes, we pretty much just focused in on fuels, weather, topography. But there's something else going on here. The thing about fire spread, when you really get into it, right, there's a lot of different physical processes going on there, right? There's like heat transfer and chemical reactions happening and airflow, and all these things are combining to produce the rate that the fire actually spreads at. And if you want to kind of group all those little pieces that go into how a fire spreads, you could do it like this. This would be one way. So you could talk about the heat transfer. So when a fire is spreading there, you have an existing fire, there's some flames of a certain size, certain geometry, like how long the fire line is or not, if it's curved or not, things like that. All those things are going to affect the heat transfer. So you have radiant and convective heat transfer going on, transferring heat from the burning area forward to the unburned area. Another piece of this whole process is you have what we call ignition there. What we mean there is what's happening to those unburned fuel particles, like say some pine needle sitting out in front of the fire receiving all this heat and having moisture in it, and as it receives the heat, it's drying out and it's heating up to some, say, ignition temperature. So that's a big piece of this whole process. And then the last piece is once those fuel particles ignite, how do they burn? So when they ignite, what's happening is they're basically reacting with oxygen in the air. It's an exothermic chemical reaction that's happening, and that's releasing energy. How fast those things burn or not, and how they release their energy, essentially, that goes into how big the flames are going to be. And that then feeds back into the heat transfer piece. And so you can see it's a coupled system, and everything there depends on everything else. If you, for some reason, somehow increase the heat transfer, that's going to increase like how fast things ignite. But if things ignite faster, you're going to get more combustion. More combustion means the flames are bigger, right? You're going to get more heat transfer. So every piece is connected to the other pieces, and they all depend on each other. And a lot of that, there are these lags in the system and things. And that process is what gives you, say, when you start a fire and it starts out moving slowly and it gradually accelerates, or then maybe goes to some equilibrium spread rate over time. All those processes are combining together to cause those kind of changes in the fire behavior. Let's talk about a few other things. This is a really important one, and this is one you should, as a firefighter, try to visualize these things in your head, because it'll help you when you're out there on the ground actually watching a fire burn, trying to understand what's going on. So let's talk about some fluid dynamic behaviors of fires. So when I say fluid dynamic, airflow, air is considered a fluid, at least to us engineers. We're talking about the airflow around a fire. One thing we're going to talk about is entrainment, and this is a really key piece, and you'll see this kind of come up later in the presentation in a few different ways, so focus in on this. If we have a fire burning there, this is kind of a side view looking at a fire, say it's a campfire maybe. We're looking at this fire, it's producing these hot gases. These gases are buoyant, they're lighter than the surrounding air. In the gravity field that we have on Earth, that means those hot gases are going to want to go up, but they can only go up if air can come in to replace that air that's leaving going up. In a case like this, most of the air that's going to come in to replace the upward moving air is going to come in from the sides. And in this case, everything's cool. Air can easily come in from both sides. It goes up. The fire acts kind of normal, I guess you might say. The flames stand up. Now let's talk about what happens to moving air if you restrict some of the entrainment. Let's say in a lab we had a nozzle shooting a jet of air just out horizontally from left to right there, out into like an open room. So if we have a jet shooting air out, there's actually a low pressure that forms there. And just like we saw in the fire, air wants to be entrained in from both sides, and that jet is just going to shoot straight out if there's no buoyancy or anything. If we look at that same jet, but we put solid surface next to it, what that surface is doing, that curved surface there, it's blocking the entrainment from one side, but we can still entrain from the other. And you get a pretty interesting thing with that jet. That jet doesn't go straight out anymore. It attaches to that surface. And it's because you have no entrainment from the surface side, but the other side, the top side, you're getting a bunch of entrainment. And you can think of that entrained air, it's kind of like the momentum of that pulling in is curving that jet down along that surface. So there's entrainment restriction because of that wall there. Now let's talk about how this might act on a fire burning on a slope. So again, we have a fire burning here. This is a side view. Like we said before, hot gases want to go up. They can only go up if they can suck air in from the sides to replace that air going up. But we have a problem here. The ground is right there on the upslope side. So that ground is at least partially blocking some of that entrained air. Now that you saw that last slide, you can probably imagine what's going to happen here, right? That flame and plume is going to be tilted down. It's going to kind of tend to stick to the slope. And what do you think is going to happen when those flames stick to the slope on the uphill side? You're going to increase heat transfer to the unburned fuel up there, both convective heating, hot gases flowing up there, and also radiant heat transfer. That's why fires burn faster up slopes than they do downslope. It's because of that restricted entrainment and the tilting of the flames. So here's a laboratory experiment I did just to show you guys. So we have a fire burning, and I took like a piece of plywood and blocked the entrainment on one side of the fire. And you can see how, when there's no entrainment blockage, it stands straight up like you'd expect. But when you block the entrainment on the left side here, the flames tilt and stick towards that slope. And I think I tilt it down here, and you can see it. It's sticking to the slope. Here's another example of this. So this was a fire up in northwest Montana, burning in slash. We built up a big, huge row of slash there. And this is basically simulating like a big line of fire burning cross slope. So that's a steep slope we're looking at. It's steeper than it looks. And you see when we ignited it, there's some holes in that line of fire that are going to fill in. Before they fill in, entrainment is kind of able to come into those flames from all sides and even through those gaps where those holes are. But as soon as those gaps fill in and you have a really good long line of fire, if you think about it, the middle of that line can't really entrain from the sides at all, right? Because there's other fire there that's entraining itself. So in the middle, at least, it can only entrain air from the downhill side that we're looking at here or the uphill side. And as we saw before, the uphill side has some blockage because of the slope. This is the same fire from above looking down. I just want to point out again that there are a few holes, and it kind of goes off the screen to the right, but there are a few holes in the flames at first. And as we first ignited it and there were still holes, the flames really stood up. But as those holes fill in and you get a good continuous line of flame, you start getting restricted entrainment, and it tilts down and it tilts up the slope like you see here. So this last view is going to be from the side. And this, I think, shows it the best. Right now, we just ignited it. There's still those holes there, and you can see the flames are pretty much standing straight up. If we wait a little while, you'll see they tilt more and more. As soon as those holes fill in, it's going to start tilting. By the very end, it's really, instead of straight up, the flames are almost completely parallel to the slope. A really huge difference in the forward heat transfer there, the stuck flames versus the straight standing up flames. And you can use this idea, for example, when you're prescribed burning, when you're dragging a drip torch around. If you drag a continuous line of fire versus some dots, you can really affect how the flames are tilting down or not, standing up, and affect a lot of the fire behavior. So let's talk about one idea now. So something that in the fire protection engineering community, so like structure fire community, research community, they call it the trench effect or chimney effect. I'll show you what this is in a second. It's also an entrainment related thing. Let's just think about this concept. So here we have a canyon, like say a steep, kind of deep, narrow canyon. We have a small fire burning on the sidewall. And so if we think about the airflow like we have been, that hot air is going to want to go up. That little fire is able to mostly entrain air from all sides. It's on the slope, so there will be less entrainment from the upslope side, more from the downslope side. If there's no wind or anything here, we'd mostly expect that to go up. But the one point that I want you to really think about and watch is how big of an area is that small fire drafting, sucking air in from? And compared to the scale of the canyon and the size of the canyon, it's a pretty small little area that it's sucking air in from. And so it's not sucking air so hard from such a big area that the other canyon wall is blocking it or anything for this small fire. So in this case, spread's going to go upslope. Let's think about a bigger fire. Bigger in the sense that it's getting close to kind of the scale of the canyon, the distance across the canyon, let's say. It's getting to be in the range of that size. And so now let's start thinking about entrainment, right? The hot air wants to go up. It can only go up if air can come in and replace it from the sides. But now that big fire is trying to draft air in from a large area, and those canyon walls are really starting to affect that entrainment. Can't draft air in from the left side very well because that left wall of the canyon, the right side, the slope is there. So it really is going to be restricted to entraining air either up the canyon or down the canyon. In this case, I drew it so air is mostly coming up the canyon at the fire. And what do you think that's going to do to the fire behavior? This could be a case where the fire actually runs up the canyon, even though the slope it's burning on, just the slope would say maybe it burns up, straight up to the right. Anyways, this is a thing to consider, and you've probably, if you've been dragging drip torches around a lot and burned through like little gullies and things, maybe you've seen this effect in a kind of a small scale. Just a few names of tragedy fires where I would argue that this kind of chimney effect may have happened. The 30-mile fire is a really good example. That lower left image is the fire progression of the 30-mile fire. There was really no strong wind or anything on that fire, but it made a hard up canyon run. And it didn't make that run until it had grown from the bottom of the valley into a large fire. So it was, of the scale of the size of the canyon all the way up the canyon wall. And it was even on the other side, which they don't show very well there. But one last one here when we're talking about entrainment reduction. So what about two fires burning next to each other? So we have a bigger fire on the right and a smaller fire on the left. Remember, both of these fires, in order for the buoyant air to go up, we want air to come in from the sides to replace it. But in the middle there, between the two fires, you can see those two fires are going to be competing for air. And if you have a really big fire and a smaller fire, the bigger fire is going to be sucking air harder. And you could get something like that, where maybe the air draft from the big fire is sucking the smaller fire towards it. We'll switch to a new topic, but before we do, I just want to emphasize again, really watch the smoke. We're lucky because fires produce a lot of smoke, so you can actually see a lot of the airflow and fluid dynamics. Think about that when you're watching a fire and trying to decide why it's doing what it's doing. Remember that buoyant air needs to be replaced by air being sucked in, being entrained in. So let's talk about fire, and vorticity is a fancy word for basically rotating air around fires. So here we're talking about things like fire whirls, fire tornadoes, and what we'll call rotating plumes. First, let's talk about rotating air and how does that happen. One important thing to know about that is, how does this rotating air form? Where does it originate from? And one of the best places for rotating air to originate from is when you have wind shear. If you have two streams of air that are moving in opposite directions like this, it can cause these little swirls to form at different scales, depending on the scale of those two air masses shearing like that. You can also get wind shear like this. Wind moving in the same direction, but you have like a fast wind and a slower wind. That's also shear, and that can also cause rotation. Where would we expect to see masses of air that might be moving in different directions or different speeds? If wind is flowing over a mountain or a ridge, just like a rock in a stream is going to have a bunch of eddies and things in the wake back there, you're going to get the same thing in the atmosphere if you have an obstruction like a mountain. So on the back side is a really good place to find these little swirlies. Sometimes the atmosphere can set up in a way that you can get waves forming downwind of a mountain range like this, just like waves in the ocean sometimes can break coming on shore. A lot of times they can break, and those breaking waves can actually cause a lot of swirliness as well, a lot of vorticity. On the top right can also happen around weather frontal passages, so like cold fronts and things. A lot of times those fronts are pretty large scale, but there is a lot of vorticity around some of those fronts. Maybe the smaller scale type fronts like a gust front from a thunderstorm or something. And last, let's say it's nighttime diurnal drainage flow and you have a few drainages coming together. That would be a good place to get a bunch of shear from wind from different jets of air coming together in different directions. Now we know out in the ambient atmosphere you can get a lot of these little swirly rotations for different reasons. How does that form into a fire whirl? Fire whirl can be pretty strong, or a fire tornado. This idea of vortex stretching is a really important one when it comes to concentrating and enhancing the speed of the spin of a vortex. Say we had a slowly rotating vortex like on the left there. If we could somehow stretch it along its axis, just like stretching a piece of Play-Doh, it's going to shrink in diameter. And if you take a vortex that's spinning over, say, a wide fat vortex and stretch it to be a skinny tall vortex, it's going to spin much faster to conserve angular momentum. So basically, the kinetic energy that's contained in that area has to be conserved. And so when you stretch it, it just concentrates that energy basically into a smaller area and it moves faster. Turns out a fire's buoyant plume, so the air that's accelerating upward above a fire because it's buoyant, it's accelerating, meaning it's increasing its speed with height, at least for a while. That causes a stretching motion. And so if you have a big vortex that moves over, say, a fire, a buoyant plume, and it stretches the vortex, that's how you can get a fire whirl. And the last point to make here is just that it can be a very large area slowly rotating, but you can really consolidate that down into a tiny little area of highly concentrated rotating kinetic energy. One of the best places to see a fire whirl is on the lee side of a mountain or something where you get all those swirlies naturally. You can get fire whirls with no wind or anything. Actually, the fire's buoyancy, that drafting that we just talked about, if in a certain way, can actually cause jets of air to come in and cause shear. Fire can actually cause its own rotation. So this is a little lab experiment we did where we ignited 5 different fires near each other. And so all these fires, and they're oriented in a very specific way. Basically, the outer 4 fires are limiting the entrainment to that center fire, and they're limiting it to only come in through those few gaps there that you see. So that entrainment that does come into that center fire comes in kind of a shearing motion. So let's move on to the top view here. Play this and you'll see the fires ignite here in a sec. So that's how you can get a fire whirl with no ambient wind or anything. The fire basically is generating the wind that causes the shear, and then you get the stretching and it spins up to a fire whirl. And those arrows show you those gaps that we built here. You might be thinking that this is in a lab under these really specific geometry situation. Out in the real world, you could get something like this if you get like an area of mass spotting, where you get a bunch of spot fires that ignite and they're all starting to grow, and they start to get big enough and close enough that they're interacting. And if you ever see several fires like that starting to compete for air entrainment, then be careful, because you could get some really odd behaviors, including fire whirls or just really tilted over flames and things like that. So rapid spread rates. So now let's move on to talk about counter-rotating vortex pairs. There's been a really well-studied thing at lab scales for quite a few years. Turns out if you have just a buoyant plume from a fire, but it could even be like a helium plume, just a buoyant plume on flat ground going up, and then you put a cross-flow wind on it. That cross-flow wind already contains some rotating air basically in it. And without getting into too many details, the interaction between the cross-flow wind and the buoyant plume, this occurs a lot, of different varying strengths, but it causes 2 big counter-rotating vortices to form on the lee side, the downwind side of the fire plume. And you can see this a lot if you know what you're looking for. A lot of the time, it doesn't really affect the fire behavior too much, but sometimes those things can spin up under the right conditions, and we believe at this point there's kind of just the right amount of wind versus the buoyant flow speed, but that's still an area of active research. But these things can get to be fairly strong, and they can get to the point where they can affect the fire behavior, like how the fire is actually spreading, or even sometimes dominate the fire behavior. This is a video it was called the Route Fire in California in 2021. It was an entrapment fire. This is video of the fire burning. The ambient wind here is blowing straight towards the camera. The fire's coming at us. Watch the rotation on this thing. This rotation really dominated the fire behavior on the head of the fire, and it ended up causing kind of a tongue of flame to be curled around with that wind and come down and cut these guys off from their escape route out towards the camera. We'll play that one more time. You can see that fire running down slope hard, and again, the ambient wind is coming straight at us, straight down the road. Fire's kind of moving in a down slope hard and 90 degrees from the ambient wind, and it's all because of that big counter-rotating vortex. Now we're going to really switch away from fluid dynamics and airflow. This whole discussion is about fire behavior phenomena that happens that's kind of outside of what our models can do right now, can predict. And so I just wanted to touch really quick on the topic of live fuels. What you're seeing right here is a Doug fir branch with some live needles, high-speed camera on the left, on the right is infrared. These needles are being exposed to high-temperature air, like flame temperature, but air, so not combusting like a flame. We have an apparatus in our lab. There's very hot air shooting over these. These needles are heating up rapidly, and you see some really interesting behaviors here. And you don't see these behaviors if you put like a dead fuel over there. When you think about live fuels, something like at least half of it is water. The question is, how do those things even burn? Because dead fuels, it doesn't take too much water, and it's hard to get them to burn. But these much wetter live fuels can burn. And this is just a little bit of insight into our thoughts that there's something completely different when it comes to heat up and ignition of live fuels that happen compared to dead fuels. There's so much water in there. Our initial thought is that these needles are heating up rapidly. They are built structurally to hold on to water as much as they can. We think what's happening is the water inside there eventually gets to a point where it's like boiling, and there's a lot of pressure building up in there. That water is trying to expand, but the cell walls and the structure of the needle are holding onto the water as hard as they can until they can't anymore, and the walls burst. And you see those jets of flame shooting out. Those are actual explosions of kind of the walls of some of those needles blowing off. You even notice how violent they are. The needles get shot back as the jet goes out. In a nutshell, what this is telling us, again, there's so much to learn that we don't know about live fuel, but we really don't know what's going on with live fuels. You know, I know the Rothermel model, you can put in live fuel information, loadings and moisture contents and choose fuel models with live fuels, but our knowledge of how that's really working is very, very limited. So just be real careful whenever you're dealing with fire spread in live fuel, and if you're measuring fuel moistures and things, we really don't understand what's going on there. Just a quick summary. Some of the things we talked about, we're talking about fire line acceleration. So when you ignite a fire, even though the fuel weather topography are the same, the spread rate can change for different reasons, heat transfer reasons and things. Fire line length effects I put there, point ignition versus a big solid line ignition, same fuel weather topography, but you can get different spread rates for various reasons, you know, because fire spread is really this kind of coupled system that's evolving over time. And every little piece in there affects the other pieces. The other point that we talked about a lot is just entrainment, and hopefully those were some good visual things to look at to help understand what we mean when we're talking about entrainment and how that airflow that's happening around a fire, and when you get restricted entrainment and things, how that is affecting fire behavior. And again, that's really outside of what our current models can do. Another point, the wind shear and rotation, right? So anytime you have like air masses that are passing each other that are causing wind shear, you can expect to see rotation. And if you have a fire burning there, especially an intense fire, that plume can stretch the rotation and cause a fire whirl. And then the last is just that live fuels we know burn very differently than dead fuels, and the models that we currently have don't really handle that well at all, and there's still a lot to learn about that. So that's the end of this presentation. A quick plug-in for a new app that we just developed that I think will be really useful to you guys, both for when you're out like on a wildfire and also you guys doing prescribed burning. It's an app called the Fire Weather Alert System. So it's a mobile app. You can get it on your phone, iOS or Android. You just go to the Google Play Store or the iOS store and search for Fire Weather Alert System. You got to make a username and password, but should be pretty straightforward. So what does the Fire Weather Alert System do? It's basically a weather app tailored to firefighters. So a couple of the main features of it. The first one is that it has an alerting system built into it, a custom alerting system. So you as a user can set a watch area, we call it. There's a map interface and stuff, but you can basically set your location and a watch radius around you. So maybe you tell it, watch the 10-mile radius around me, and then you tell it what kind of weather you want to be alerted to, like high winds, like winds over 20 miles an hour, or relative humidity below 15%, or whatever you choose. The presence of a thunderstorm or a lightning strike nearby. There's several different things you can choose. And then the system, so you set that in the system and say go, give it a duration, like the next few hours to watch. And then the system watches weather forecasts, but also measurements like RAWS stations, radar. We're working to get the lightning detection systems into there, maybe some satellite data as well. But it watches a bunch of different systems and then sends you an alert, currently through a text message or an email. In the next release, you'll get an alert, like an in-app alert on your phone, that there's a watch. And then when you get that alert, you can go in there and dig into it a little deeper. It also gives you easy access to a lot of data out there that you will find useful. On your phone, you can look at a map, see your location. You can turn on the RAWS layer, see all the RAWS that are around you. Click on a RAWS, go look at the data that's been measured right there on your phone, which is really hard to do until this point. Soon we'll have a lightning layer in there. We have radar. There's a bunch of different things in there. There's a way that you can get to the zone weather forecast. You can turn on the map of the fire weather zones so you can see that, because you might be on a dispatch or something and you don't know the zone numbers they're reading off the radio. You can turn that layer on and look at that. Anyways, just wanted to put a quick plug in for you there. Go check that out if you're interested. Give us feedback too. That's the end of my presentation.